Hi, my name's Caitlyn Barrett. I'm in the 3D CAD and Engineering Documentation Section 2 course.
And my name's Collin Anderson, and I am in the EGR 305 Section 1 course. And this is our final project. Alright, so we're going to start off with our project overview. The objective of this project was to create an assembly in CATIA utilizing at least one advanced workbench. Both Caitlyn and I decided to create an assembly of a toy train and utilize the DMU kinematics workbench to show its motion along a track. On the right, you can see a toy train that really inspired us for our design.
Getting into the team dynamics, Caitlyn was responsible for the parts, drawings, and subassemblies related to the train, while Collin was responsible for the parts, drawings, and subassemblies related to the track. Both team members then got together to create the final assembly and the kinematics simulation. Shown on the screen now is the Gantt chart that the team created at the very beginning of the project. This Gantt chart is the schedule that the team followed in order to complete the project. The top shows the deadlines while the side shows each major task. These tasks included completing the parts and their associated drawings, completing the subassemblies and their associated drawings, completing the full assembly and its associated drawings, completing the kinematics, completing the report, and finally completing the PowerPoint and the video. All of these listed items were completed in just 5 short weeks.
Now let's move on into our subassemblies. The track itself was not complex in nature. The hardest part of this subassembly was researching the specific dimensions of the track like this. Once the dimensions were found, the rest of the design really fell into place quite easily. The whole track subassembly consists of 2 unique parts. The first part being the straight track piece. This was created by simply making a profile in the part design workbench and then extruding said profile. The addition of the male and female connections came after. The curved track piece was a little more difficult, but not too far-fetched. It started off the same as the straight track piece, but instead of extruding that profile, a curved line was drawn. The rib command was then utilized to make curved extrusion. The hardest thing about this part was making sure the curve wasn't too steep. The interesting thing about these two pieces that make up this subassembly, as you can see, there's 4 straight tracks and 4 curved tracks. Each piece has the same exact cross section, so these are very easy to model comparatively. These did not require too much time.
The next subassembly that we will be discussing is the locomotive subassembly. This subassembly is made up of 9 unique parts. These parts include the train body, stack, hitch peg, hitch magnet, cow catcher, 4 wheels, 4 linkage pegs, 4 axle pegs, and 2 linkage arms. All of those parts that were just listed are made of plastic, excluding the hitch magnet, which is made of iron. This design was made from the online reference that is displayed on the screen. This online reference showed the dimension drawings of the parts that make up this subassembly. Some alterations and assumptions needed to still be made, however, because these drawings were not always perfect. The final subassembly that was created for this project was the passenger car subassembly that is shown on the screen. This subassembly is made up of 7 unique parts. These parts include the body, the hitch peg, the hitch magnet, 2 axles, 8 wheels, 4 connectors, and 8 connector pegs. Just as with the last subassembly, the reference that was used to create this subassembly is shown again on the screen. This online reference is just like the other because it shows all the dimension drawings of all the parts that make up this subassembly. Some alterations needed to be made to have the parts better fit for our intended design. For example, the body was changed to only having 1 door in the front and then a closed back rather than a door in the front and another in the back. Some dimension assumptions also needed to be made because many of the drawings were either missing dimensions, too blurry to read, or both.
So now we're going to move on to the final assembly. The final assembly shows the locomotive and the train both situated on the track. What we used for this was when we built the track subassembly, those are simply connected by offset and contact constraints for each individual track. So there is a contact constraint between the wheel and the indented portion of the track, as well as an offset constraint between the back of the passenger car and the back plane of the track.
We will now discuss the advanced workbench that we decided to utilize for this project. The team decided as a whole that the advanced workbench that they wanted to use for this project was the digital mock-up kinematics workbench, and that was used in order to simulate the motion of the train along the tracks. So the first step in doing this was to remove the wheels, the linkage arms, and the linkage pegs from the locomotive subassembly, because these parts were designed to be the rotating elements, therefore they needed to be constrained as joints within the kinematics workbench. Next, a new track was actually created of only the straight pieces, because the time constraints on this project, as well as the inexperience using this workbench of the group members, did not allow for them to simulate the motion of the train on the circular track subassembly. Getting into the kinematics, first all the parts were inserted into a new product file, including the new straight track subassembly, the full train subassembly, and then the individual parts of the locomotive that had been removed from the subassembly. Getting to the joints, the first joint that was applied were the revolute joints to the wheels of the locomotive. The two lines that were chosen for this joint were the axis of the wheel and the axis of the axle peg. The two planes that were chosen were the inside face of the axle peg and the front face of the hub of the wheel. The two back wheels on the locomotive were set to be angle driven so that the model could easily be simulated. Some more revolute joints were then applied to the linkage arms of the locomotive. For these ones, the two lines that were chosen were the axis of the hole on the linkage arm and the axis of the pegs on the locomotive wheels. The two planes that were chosen were the front face of the peg and the back face of the linkage arm. This was performed for both linkage arms, as each one connected to two of the wheels. The next type of joints that were applied were rigid joints, and these were applied to the linkage pegs. To constrain the pegs in the correct locations, the assembly design workbench was entered and the pegs were constrained to the linkage arms with a coincidence in contact constraints. The digital mock-up kinematics workbench was then re-entered and rigid joint was applied by selecting each linkage peg and its corresponding wheel. The final type of joint that was applied was a length-driven prismatic joint, and this was applied to a hidden line drawn on the train assembly to the inside line of the indented portion of the track. Applying this joint allowed for the simulation of the train moving along the tracks. After creating all of these joints, the degrees of freedom dropped to 0, therefore the simulation was able to be run. The simulation settings for the angles of the wheels were set to negative 720 degrees to 720 degrees in order to set an appropriate speed of the wheels. And the length for the prismatic joint was set to negative 20 to 130 in order to have the train move from end to end of the tracks. The simulation was then run and exported as JPEG images utilizing the Photo Studio workbench. The following video shows the final simulation. In conclusion, the project was successfully completed. As stated earlier, the objective of this project was to create an assembly in CATIA and utilize one advanced CATIA workbench. The team accomplished this objective by creating a toy train assembly and then utilized the digital mock-up kinematics workbench to simulate the train moving along its tracks. Through completing this project, the team discovered the best approach to take when tackling future projects. At the very beginning of the project, the team created the Gantt chart that was displayed earlier in the presentation. Creating this Gantt chart allowed the team to set goals towards completing the project, which allowed them to better manage their time. Going forward, the team will continue to create Gantt charts when working on projects. When the team first came together to create the final assembly, they realized they referenced different sources for the dimensions of their parts. Therefore, one was working in millimeters while the other was working in inches, and their parts did not fit together. After taking the time to correct this mistake, the team realized that in the future they will ensure the entire team is referencing the same documents. All in all, the team is happy to have successfully completed this project because they learned a lot along the way.